This is the PowerPoint presentation for the first of a set of modules addressing training needs for Cone Beam CT. As this is module number 1, we assume that it is likely that this is the first module that you will encounter. Therefore, before we start looking seriously at the subject of this module, we will give a broad introduction to the subject and lead you into the learning outcomes. X-rays have been used to produce images ever since Röntgen discovered X-rays in 1895. The drawing on the top left illustrates Röntgen producing an image of the bones in his hand with a very early form of X-ray tube. The first dental X-rays were taken within weeks of Röntgen's discovery. The image on the right is an example of a very early dental radiograph produced by Volkow in Germany in the early weeks of 1896. The story of X-ray use in dentistry is a very slow evolution. The first dental radiographs were taken in 1896, as I said, but it wasn't until the 1910s, the 1920s, before the first manufactured dental X-ray sets began to appear. And indeed, it wasn't until the 1930s before X-ray sets became widely available to dentists. Up to that point, equipment was very primitive, homemade apparatus, such as you can see on the top left. In contrast, on the right, you can see a piece of dental X-ray equipment from the 1930s that is beginning to look something more like normal modern X-ray equipment. But there's still a long way to go before we see what we have today. The first machine-wrapped film came in 1913, with ultra-speed film arriving in 1940, the long cone technique for taking intraoral X-rays in 1947, and E-speed film in 1981. So developments in dental radiology have indeed been evolutionary, not revolutionary. Today we have 65 to 70 kV constant potential X-ray sets, a longer focus to skin distance, rectangular collimation, the use of film holders, fast film, and increasingly the substitution of film by digital systems. One of the challenges that we face in conventional two-dimensional radiography is interpreting what is really a three-dimensional object. To try and overcome this, dentists have used parallax techniques, using two radiographs taken at slightly different angles. While this is an established method, it still doesn't quite give us the three-dimensionality that we would love to have. Today, however, a new technology has appeared called cone beam computed tomography that offers us three-dimensional imaging in the dental practice. You only have to open a dental magazine or attend a trade exhibition at a conference to know that there are a multitude of CBCT equipment around on the market. This is the subject of this training module. The learning outcomes that we intend to achieve at the end of this module are as follows. In terms of knowledge and understanding, that you understand how X-rays interact with material, that you have a knowledge of the concept of the imaging chain from initiating the X-ray exposure through to display of the image, that you understand the difference between two- and three-dimensional imaging, and that you understand the very basic structure and function of a CBCT machine. In terms of practical skills and abilities, there are no particular learning outcomes for this module. We will see those appear in the second module. And our overall judgment and stance is that we attain an excellent understanding of the fundamental basis of all X-ray imaging. So, Cone beam CT. One of the first things to mention is that this name is not universally used. Alternative names exist, such as digital volumetric tomography, or DVT, and more recently, digital volumetric reconstruction, or DVR. This can be very confusing, but throughout these modules we will stick to the most widely used term, cone beam CT, or CBCT for short. To understand how CBCT works, it is essential that we understand the fundamentals of X-ray based imaging. So we're going to start from that point. The first thing to say is that it's helpful to understand the concept of the imaging chain from the initiation of the X-ray exposure through to display of the image. Here we see this diagrammatically. On the left, the X-ray machine, the patient, then the film or digital detector, and finally the way we display the image. In terms of the X-ray machine, factors such as kilovoltage, milliamperage, and the time will influence the image that is produced. The projection and the position of the patient will obviously influence what is seen on the final image. How those X-rays interact with matter are of importance in image production, but also in terms of radiation protection. The method of image acquisition, is it two-dimensional or is it three-dimensional? And if it is three-dimensional, whether it's fan-shaped or cone beam technology. Let's start with the X-ray source. This is a simple X-ray source from a conventional dental X-ray set. The diagram on the left is equivalent to the photograph on the right. What you see is an evacuated glass tube. At one end of the tube is an anode, and at the other end is a cathode. Function: electrons stream from a filament in the cathode to a target in the anode, where they produce X-rays. In order that the X-ray tube functions, we need a power supply to heat the cathode to generate the electrons, and secondly to establish a high voltage potential difference between the anode and cathode to accelerate the electrons towards the anode. Let's break the X-ray tube down into its components and look at them in more detail. Let's now look at the X-ray tube in more detail. At one end is the cathode. Looking at the image on the left, you will see in the center of the cathode a thin wire coil. This is made of tungsten. When the exposure button on an X-ray set is pressed, this heats up and gives off electrons. At the other end of the X-ray tube is the anode, which is made very positively charged by the kilovoltage across the X-ray tube. The result of this is that the electrons produced at the cathode gain an enormous amount of energy and pass rapidly across the X-ray tube and hit the target on the anode. This produces X-rays, although in fact most of the energy is converted to heat. This heat is conducted away down the copper of the anode. An alternative X-ray tube source is a rotating anode X-ray tube. This is used in larger pieces of X-ray equipment, typically used in medical radiology. As we will see later on in this module, at least one cone beam CT machine uses a rotating anode source, and it is perfectly possible that in the next few years more cone beam CT machines will use such a source of X-rays, so we are including it here for completeness sake. The main difference between this rotating anode tube and a fixed anode tube, such as we saw on the previous slides, is that the anode is of disc form, and this rotates rapidly The point of this is that there's a larger effective target surface which can be used to generate X-rays. This helps in dissipation of heat and also improves the output of X-rays from the X-ray source. How do we control the amount of X-rays produced in an X-ray machine? Well, the first parameter that we can use is exposure time. This is straightforward and easy to understand. The longer the exposure time, the greater the number of photons generated. The second parameter is the current, measured in milliamps. This is actually the flow of electrons across the X-ray tube. The number of photons of X-rays produced is directly proportional to this tube current. The final parameter is the tube voltage, or kilovoltage. Here it's expressed as kVp, where P stands for peak kilovoltage. Increasing the kVp increases the energy of each electron when it strikes its target in the anode of the X-ray tube. The consequence of increasing the kilovoltage is to not only increase the energy of the X-ray photons, but also to increase the number produced per unit time. Let's just think for a moment about the projection and positioning part of the imaging chain. At the very start of this module, we use the term shadow picture for a radiograph, and that still is the same concept to understand with simple two-dimensional imaging today. But let's think about a factor of magnification. X-rays arising from a point source diverge according to something called the inverse square law. If we double the distance from the source of X-rays, we quarter the intensity of those X-rays. This is important to understand in the concept of magnification of images, but also in radiation protection, where distance affords a great benefit in reducing exposure to X-rays. Thus, in conventional X-ray imaging, we have an X-ray source, an object and an image receptor. The beam diverges from the source of X-rays and produces a magnified image. How do X-rays interact with matter? Well, they do so by a process called attenuation. This consists of three different interactions between X-ray photons and electrons. The first of these is called a photoelectric effect and is a pure absorption. It results from the interaction of an X-ray photon with a tightly bound inner orbital electron of an atom. The second effect is the Compton effect, where the X-ray photon interacts with an weakly bound outer orbital electron. Here there is both absorption of X-rays and some scattering of X-rays. Finally, we have pure scatter or coherent scattering produced. All these three interactions will occur when we X-ray a patient. Photoelectric effect is the one that gives the highest dose of radiation to patients, the highest transfer of energy, but there is no scattering of X-rays. The Compton effect has, as we said, this combination of absorption and scatter. The amount of attenuation that occurs when we X-ray an object depends on three factors: the thickness of that object, its atomic number, which is essentially the size of the atoms, and also the physical density of that object. On this simple bite wing radiograph, you can see the metallic restorations being very radiopaque because most, if not all, the X-rays that pass through the patient have been absorbed in these restorations. And this is a consequence of the high atomic number. If we move on to image acquisition, we all know that there's a vast range of different methods of image acquisition, even in dental radiography. If we're dealing with analog image acquisition, we have film or film intensifying screen combinations. While for digital image acquisition, we have CCD and CMOS detectors, phosphor plates, and we also have flat panel detectors and image intensifiers. These last two have traditionally been more relevant to medical radiology rather than dental radiology. But because of the advent of cone beam CT, dental radiography now has to encompass these also. The final stage, of course, in image production is display of the image. And with conventional analog images, we use transmitted light through film on a viewing box. But for digital imaging, which includes cone beam CT, we rely on computer monitors in order to interpret our image. Having dealt with the very basics of X-ray imaging, let's try and move a little closer to the subject of this module. But we'll start with the concept of computed tomography. The word tomography derives from the Greek word for a part or a section of a patient. Computed tomography was developed in the late 1960s by two scientists, Godfrey Hounsfield and Alan Cormack. It involves the collection of digital multi-projectional X-ray data which are subjected to something called a reconstruction algorithm. And the first patient was scanned with a CT scanner as early as 1971. Here's an X-ray CT scanner, but here diagrammatically is what's happening. X-rays are passing through the patient and being captured by X-ray detectors around the patient. This X-ray transmission data is manipulated by a computer into hundreds and thousands of projections through the patient. An image can be then constructed using the X-ray absorption calculated for each volume element of the patient, called a voxel. Here's part of a CT scan series, and we see multiple slices through this patient's maxilla. The X-ray absorption of each voxel is closely related to its density in CT scanning. This is related to the linear attenuation coefficient of particular materials. Each three-dimensional volume element or voxel of the patient is represented on the computer screen by a two-dimensional pixel. If we look at this close-up picture of the scan on the top right, you can see the individual picture elements making up part of the image. Each pixel has a grayscale value. This grayscale value relates to its density using something called Hounsfield scale, which traditionally runs from -1000 to +1000, although in some CT scanners this may be extended to -2 to +2000 or other ranges. Let's try and explain what we mean by this Hounsfield scale, because it is relevant in some ways to cone beam CT. Here is the Hounsfield scale based on a -1000 to +1000 range. In displaying images, we need to be able to differentiate between structures of different density. So on Hounsfield scale, as shown here, air is given a Hounsfield number of -1000, whereas dense bone is given a Hounsfield number of +1000. This represents the range of densities within a patient. Water, which is typically representative of soft tissue, is given a Hounsfield number of 0. If we expand this central point, we'll see that within the soft tissues we have a range of -100 for fat, through to plus 100, where calcification will start to be apparent. What is the significance of Hounsfield scale in clinical practice? Well, the grayscale can be changed by compressing it over a narrow range of densities, using a narrow window as it's called, or the full range of densities, a wide window. To look at subtle soft tissue differences, you would select a narrow window width around the centre of Hounsfield scale. If we are only interested in bony images, then we would use the widest window. This allows us to see bone particularly well. The CT scan at the top has a reasonably narrow window which allows us to see soft tissue differentiation. So you can pick out muscles, you can pick out fat and bone at the same time. Whereas the image at the bottom, which was taken for dental implant planning, uses a wide window in order to differentiate bone from everything else, but we do lose contrast within the soft tissues. Digital data can be reformatted in any way desired. This is called multiplanar reformatting. The scan at the bottom right shows someone's temporomandibular joint reconstructed from the axial scan into a sagittal scan. Unfortunately, the image resolution is less than for axial images because of the voxel thickness in CT scans. In order to overcome this, we can produce our scan sections more thinly, and this will give a better reformatted image, but can increase the radiation dose dramatically. What are the dental and maxillofacial uses of CT scans? Well, they've been used widely in hospital practice for trauma, tumours, and for the temporomandibular joint. But probably where most dental practitioners would come across CT scans is in its use for dental implant planning in order to produce cross-sectional images of the jaw to help in selecting the most appropriate size and length of implant to use on a particular patient. Unfortunately, conventional CT scans have limited access for dentists. They cost a lot of money, and the radiation dose associated with the use of these scanners has also caused concerns about overusing them. This situation changes a little when we think about cone beam CT. So how does the technology of cone beam CT work? Well, let's think about the background first of all. Where does cone beam CT come from? Well, the history goes back to the 80s when X-ray fluoroscopic CT scanning was first devised for angiography by Rob. Micro-CT systems for imaging small specimens were developed in the late 1980s and are used widely today in research applications. Cone beam CT technology is used in image-guided radiotherapy. But the first attempts at dental CT were made in the 1980s in Japan, with dental equipment first being manufactured and presented in the very late 1990s in Italy and Japan. The X-ray source in cone beam CT is usually a low-power fixed anode tube, such as we described early on in this module. But as I said at that time, at least one machine now uses a rotating anode X-ray tube. Cone beam CT equipment comes in many shapes and sizes. In some, the patient is supine, in others, the patient stands, and in others, the patient is seated. So not all cone beam CT scanners look familiar. In terms of the image receptor, there are two main types used. The first involves an image intensifier, or to be accurate, a combination of a scintillation screen an image intensifier, and a charge-coupled device. The scintillation screen fluoresces when exposed to X-rays. This light output is passed through an image intensifier, which, as its name suggests, intensifies the strength of the information, and this passes out of the output phosphor again as light to be picked up by a charge-coupled device, which is basically a video camera chip. The second method of capturing images used in cone beam CT scanners is to use flat panel detectors. Alright, I'll say this again.
Yeah.
The second method of capturing images in cone beam CT scanners is to employ flat panel detectors. These are rather simpler in their structure, using a scintillator layer of gadolinium oxysulfide or cesium iodide, which fluoresces when exposed to X-rays. This is backed up by a pixel array of silicon transistors and photodiodes, producing an electrical signal which is in proportion to the light produced by that portion of the scintillator layer in front of the pixel. Here is a diagrammatic representation of a setup in a cone beam CT scanner. We have an X-ray source, we have a patient, and we have the image receptor. Looks very familiar to us from conventional radiography. The beam is cone-shaped. The detector is, as we've said, either a flat panel detector or an image intensifier CCD combination. When X-rays are produced, this will result, of course, in a simple two-dimensional image of the patient, the extent of which depends on the diameter and divergence of the beam. But this is where cone beam CT starts to differ from conventional radiography. In cone beam CT, the X-ray source and the image receptor will rotate around the patient's head, while a series of two-dimensional basis images are produced. The number of basis images varies from anywhere from 100 through to 600, depending on the equipment, the manufacturer, and so on. So beyond this first image, we can see that we get a series of images while the equipment rotates around the patient. This process will continue for as much as 360 degrees until we arrive back at the beginning again. As you will imagine from looking at this diagram, there will be a section within the patient where all the beams overlap, for which we have multi-projectional data of X-ray absorption. It is important, therefore, to understand that cone beam CT is a form of volume imaging. As the X-ray beam rotates around the patient, we end up with a cylinder or block of data. These data represent the X-ray attenuation characteristics of many individual voxels of tissues that lie within the cylinder. These image data must then be reconstructed using a filtered back projection algorithm so that we have accurate density information for each of the volume elements. An interesting and important aspect about CBCT compared with medical CT is that the voxels are isotropic. What this means is that their height is the same as their width, and that is the same as this depth. This is different from medical CT, where the height of voxels is usually much greater than their width and depth. The size of the voxels ranges from one piece of CBCT equipment to another, and also within an individual item of CBCT equipment where voxel size can be adjusted, but typically can range from 0.076 to 0.4 millimeters. The grayscale value allocated to each voxel is representative of the X-ray absorption in that volume element. Unfortunately, the use of Hounsfield scale is not so applicable to CBCT as it is for medical CT. So the grayscale merely relates to the density and the atomic number of materials in the patient. One aspect of cone beam CT is that there is relatively poor soft tissue contrast. As you can see on the picture on the right, the images that we get are similar to bone window medical CT scans. If we really turn up the contrast on our controls, we just start to see some differentiation between muscles and fat appearing in the CT scan. In terms of basic image display on the monitor, most CBCT scanners will give a display of 4 images at the same time. These consist of an axial image, very familiar to those who are used to looking at medical CT scans, a coronal image, and a sagittal image. Finally, you may also have what is described as a volume rendered image. In the next module, we will describe these in more detail, and we will also learn to navigate through a set of CBCT images. So in summary, we have reviewed the fundamentals of X-ray based imaging and highlighted the concept of the imaging chain. X-ray production and the interaction of X-rays with matter have also been reviewed. We know now that radiographic images are essentially shadow images produced by the interaction of the attenuated X-ray beam upon an image receptor. And we've reviewed the basics of the structure and function of cone beam CT machines.